here we use models of exponentials. Einstein said that where the laws of mathematics are certain, they do not apply to reality. And where they apply to reality, they're not certain. So here I'm giving, before I was giving you the sheer mathematics of it, and that's 100% certain, really true by definition. Here, this is more of an experimental thing. These are models, which may be accurate up to a point. For example, exponential growth of population. A population starts at p sub 0, p naught, and it grows by a growth rate of k, continuously compounded for t years, and grows to p equals p naught e to the kt. Now, the problem with this model, it's a very simple and very common model, and it says that it grows slowly for a while, and then grows very, 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 very fast until it grows huge. At some point, it outgrows the system it's in, and then this model ceases to apply. So you have to be a little bit wary about exponential models. Here we have p equals p naught 2 to the t over d. D is the doubling time of the population, how long it takes for the time for the population to double. When t increases by d, t over d increases by 1. 2 to that power increases by multiplying by 2, and the population doubles. Here we have radioactive decay. R is the radioactivity equals R naught, the initial radioactivity, times 2 to the negative t over h. T is the time, and h is the half-life, the time it takes for half of the radioactive material to decay. When t increases by h, minus t over h increases by 1, 2 to that power decreases by a factor of a half, therefore a half-life. Now here we have, we try to relate these two formulas. If p equals p naught e to the kt, then what is p's doubling time? If you have a growth rate of k, what's the doubling time? Well, if p after the doubling time t is twice p naught, then p naught e to the kd equals twice p naught. Okay, and so canceling out the p naughts doesn't matter, it turns out. It always takes the same amount of time to double no matter what it's starting from. So e to the kd equals 2. So kd equals natural log of 2. So d, the doubling time, is natural log of 2 divided by k. That's the doubling time given a growth rate of k. So for example, if the population grows at a growth rate of 5%, what is its doubling time? Well, it'll be log 2 divided by 5%, 0.05, which is about 13.86. So something growing at 13.8, at 5% per year continuously, then it takes about 13.86 years to double. Newton's law of cooling. Here, we have say a cup of hot coffee. This is actually cold tea, but never mind that. It has a temperature T at big T at time, little t, and the surroundings have a temperature T sub surroundings, and D naught is the temperature difference, T of 0 minus T surroundings. Then temperature at time T will be the temperature of the surroundings plus the difference times e to the negative kt for some constant k. The idea is that it starts at t0 and decays exponentially away to t sub s. It's an exponential decline to the surrounding temperature. And okay, here I'm going to evaluate t at time t. We're given the surrounding temperature and the initial difference, and T, the temperature at some specific given time. If you have a specific given time, T star, then we get this formula, and after a little bit of work, you get this and this and this. So this gives you the temperature at time T, given surrounding time and surrounding temperature, initial temperature, and temperature at a given time, and compared to T, the ratio. And the time to reach a given temperature, T star, is T star natural log of all this. Now, here in the Bay Area, of course, we're very intimately familiar with the Richter scale, which gives a scale for the intensity of an earthquake. So let's say that the intensity of the earthquake, measured, I think, in displacement of the ground, measured 100 kilometers from the epicenter. And this will be some standard earthquake with an amplitude of 1 micron, 10 to the negative 6 meters, very small. Okay, I assume that would be, so that would be Richter 0. Then the Richter magnitude is common log of I over S. Every time the intensity increases by a factor of 10, the Richter magnitude increases by adding 1. Decibels is much the same thing. If I is the intensity of sound in watts per square meter, and T0 is 1/trillionth of a watt per square meter, which is very, very soft sound, then the decibel measure was 10 times common log of I over I naught. This 10 means that, because that's why it's called a decibel. So 10 decibels is 1 bell, but they decided to break it down into tenths. pH scale is a measure of the acidity of a solution. This pH of 7 is neutral. Higher, higher value up to 13, say, is basic, bitter, like seawater, and lower is gives you down to 1, which is acidic. That's sour, like an acid. That's why, incidentally, why they give you lemons with seafood, because presumably the fish has the bitterness of seawater still on it. So you counteract the bitterness by squeezing it with the sourness of a lemon. And H plus is the hydronium ion, hydrogen ion concentration in the solution. Then pH equals minus common log of H plus. Now I put an asterisk here because it's not exactly hydrogen ion that's in a solution. If you have a solution of liquid, and a hydrogen ion is basically it's just a proton, and that's a subatomic particle, and it doesn't really last long in water. It connects up to a water molecule, and you get an H3O plus ion called hydronium. So okay, really, so this is really the common log minus the common log of the hydronium ion concentration. So for example, okay, so suppose something growing at 10% continuously. What's its doubling time? Well, its doubling time is log 2 over that 10%, about 6.93. 10% growth rate is 6.93 doubling time. So 3 times that will be like 8-fold, a little bit. So that would be a little bit like 21 almost years. So 22 years would be a 10-fold time. 2.6 growth rate, its doubling time is log 2 over 0.026, 26.66 roughly. If you have a 3.5% growth rate, and the initial population is 1.2 million at a time of 20 years, then the later population will be the initial population, 1.2 million, times e to the power of k, 3.5%, times t, 20, and with a bit of calculation, it's about 2,406,503. Although, frankly, those last 3 digits I doubt the accuracy of. If something had a 32-year doubling time and started out a population of 3.76 million, after 100 years, what's the population? Well, okay, it'll be population times 2 to the t over doubling time. 3.76 million times 2 to the power of 100 years divided by 32 years. And the calculator says it's about 32,802,472. And again, the last 3 digits are excessively accurate. In fact, I'd really say the best you can really justifiably say is that it's 32.8 million. Thorium-227. This has a half-life, 18.4 days. How long does it take for 80% of the sample to decay? So radioactivity equals R naught times 2 to the negative T over H. 80% decays and only 20% is left. So on this side here, we have 0.20 R naught. That equals R naught times 2 to the negative T over half-life of 18.4. Now, as ever with these decay problems, the initial amount doesn't really matter. It takes the same amount of time for a given fraction to decay. So we cancel these out. 0.20 equals 2 to the negative T over 18.4. At this point, the solution is to take log base 2 of both sides. So you get on the left, log base 2 of 0.20, and on the right, negative T over 18.4. Next step is to multiply both sides by 18.4 and minus to get T equals negative 18.4  18.4 log base 2 over 0.20. And log base 2 is log over log 2. So t is minus 18.4 log base 0.20 divided by common log of 2. And a bit of calculation, that's 42.7 days. Okay, carbon-14. You may have heard of carbon dating. It uses half-lives. Half-life, the way it works is that carbon-14 is naturally produced in the Earth's upper atmosphere by bombardment of nitrogen-14 by cosmic rays. This drifts down into the atmosphere, settles into living beings, and it takes this long, slow time decaying. Now, a freshly cut piece of wood has all its original carbon-14. But as time goes on, it exchanges nothing with its environment. So the carbon-14 slowly decays away. We are all of us slightly radioactive. Fortunately, we're adapted to that. So, all right, 5,700 years approximately. Okay, and a bone fragment is 60% of its initial carbon-14 content. How old is it? So radioactivity equals R naught initial radioactivity times 2 to the negative T over H. Since 60% of its carbon-14 remains, that's 0.60 R naught. That equals R naught times 2 to the negative T over half-life 5,700. Okay, as before, R naught cancels. So 0.6 equals 2 to the negative T over 5,700. Take log base 2. Log base 2 of 0.6 equals negative T over 5,700. Transpose 5,700 in a negative sign and get T equals negative 5,700 log base 2 of 0.6. Or expanding it a bit, negative 5,700 log base 0.6 over log 2, approximately 4,200 years. I've only recently noticed, this is a minor cultural note, but I only recently realized that in the Jewish calendar, this is the year 5786, slightly more than one half-life of carbon-14. That's a heck of a thing to have a calendar that's a carbon-14 half-life old. What is the pH of a solution with hydrogen ion or hydronium ion? Concentration of 1.7 times 10 to the negative fifth. Well, okay, you take negative the common log and get 4.77. Now, here we have a Newton's cooling problem. All right, a cup of tea is poured boiling in a room with temperature 70 Fahrenheit. So it starts off at 212 Fahrenheit, and it's cooling down to 70 Fahrenheit. It cools to 120 degrees in 10 minutes. Assuming Newton's law of cooling, when it will be 90 Fahrenheit, and what temperature will be a half hour after pouring. So here we go. Let's look at remember our formulas. T equals TS, D naught e to the negative KT. So, excuse me. T naught is 212, TS is 70. T naught is the difference. 212 minus 70 is 142. T at 10 is 120. And okay, so this is T star is 10. T at T star is 120. We use this formula here. The surrounding temperature plus D times this number to the T over T star. Let's see how it goes. That will be 70 plus 142 times 120 minus 70 over 212 minus 70, the T over 10. This being T, 10 is T star, 120 is T at T star. So that simplifies to 70 plus 142 times 0.3521 to the T10s. Okay. And a bit more calculation gives you time for a thing is 10 times natural log of 142 over T at T minus 70 over 144. So if the temperature is 90, then using this formula, you get this thing here, approximately 19.7 minutes. And what is it at time 30? Plug in 30 here. 70 plus 142 times 0.3521 times 30 tenths, 76.2. So it's about 76.2 Fahrenheit in 30 minutes. Okay.